Particles know when you're watching them. Every single thing in this world is made of particles. You, me, the light in this room, everything in the universe, if you break it down, becomes spherical spheres known as particles. But if particles behave one way when you're watching them and another way when you're not, does that mean the entire universe behaves differently when you're not paying attention? Because this isn't a theory. Scientists have actually been testing it for over 200 years. When nothing is looking, these particles behave in ways that should technically be impossible, with behaviors like existing in two places at once. But when we put our focus on them, when we measure them, when we detect them, but the second you try to see what they're doing, they switch back to the normal behavior they should have. They switch back to the typical behavior that you and I are used to seeing. So what are these two types of behavior? Where does it come from? Wouldn't it be useful to harness the ability to be in two places at once? So let's break it down. There's two types of behavior that we know particles can do. The first, where they can typically be in multiple places at once, is called wave behavior. You know what waves are. You can picture one in your head if you think about how they behave. And the second would be particle behavior. Let's start with the case for waves. The basis for all work going forward on this, an interference pattern. What does this mean? An interference pattern of a specific type indicates wave behavior. Stay with me, don't worry. So we have light, waves, firing through two slits made. And what we observe here is an interference of fringes. Imagine you throw a pebble in a pool. The wave behavior that happens is you see ripples from the pool. At each slit, waves spread out. Then the two spreading waves overlap. Where the crests of both waves meet, they add up and form a bright stripe. Where the crest of one wave meets the trough of another wave, they cancel each other out and form a dark stripe. This alternating pattern of bright and dark stripes is called an interference pattern. Because they're caused by the crests and troughs adding up, when we see an interference like this, it is indicative of wave behavior. It means that there are waves taking place here. So, the case for wave behavior. In 1801, a guy called Thomas Young followed light between two slits and found this exact interference pattern. Therefore, light is a wave, right? Easy. Physics moves on, they keep believing light is a wave. Everyone apart from this guy, Isaac Newton, he kind of thinks light is a particle. Then, about a century later, physicists discover electrons. They're definitely particles, they have mass, you can count them out one by one, they're giving particle. Okay, so far, double slit, learn what an interference pattern is. Light is a wave. We know interference pattern means waves are present. Light is a wave. Everyone apart from Newton thinks this. Newton and the physics community have beef. Now let's go on to the second side of the argument. Light is a particle. The key idea for this comes from something called the photoelectric effect. It's actually what Einstein won his Nobel Prize for in 1905. This introduces the concept of photon. What this experiment entailed. Einstein observed that if you shine light on a metal, electrons get knocked out. The question here is, what controls how much energy the electrons fly out with? If light was a wave, as we originally thought, surely brighter light, more intense light, will give the electrons more energy. If there's a bigger wave, there should be a bigger push to the electrons, pushing them out. But that's not what happened. What actually happened is more surprising than that. The color, i.e. the frequency of the light, controls the energy. It's not the brightness that would have meant wave behavior, it's actually the frequency. What does that mean? Red light, no matter how bright it is, will not knock electrons out of some metals. Switch to blue or UV and suddenly it works, even if it's dim. Einstein's explanation, he was brave enough to be different, I guess. Light actually maybe is not a wave. It comes in tiny little packets called photons, aka light particles. Wait, what does this have to do with the color knocking electrons out? How come photons give it that property instead? Well, imagine each photon has a fixed amount of energy that is set by its frequency. One photon hits one electron and gives it that energy. The electron uses some of the energy it was given to escape the metal, and that's the energy needed to break free, and then it keeps the rest as kinetic energy. But wait, this is evidence for light as particle behavior. That doesn't agree with the last century of physics we have, where we thought light was a wave. Brighter light equals more photons, but each photon still carries the same amount of small energy. So you get more electrons out, but each one with the same energy as before. Only changing frequency changes energy per electron. And in fact, this was not the only experiment in favor of particle behavior. Compton, another scientist, another Nobel Prize winner for light is a particle. You shine X-rays at electrons, The electrons go in with a certain wavelength. After hitting the electrons and scattering around, they come out with a slightly longer wavelength than they did before. This longer wavelength means lower energy, so the X-rays have lost some energy in the collision. Think of it like we're at a pool table. The X-ray photon comes in and it collides with the electron, like two pool balls. The X-ray photon gives some of its energy and momentum to the electron. Then it bounces off in a new direction with less energy. Remember that less energy is what we observed as the longer wavelengths before. A glancing hit will only transfer a tiny bit of energy, whereas a head-on hit straight through will transfer a lot. Just like pool, just like something you've seen every day, except this proved a Nobel Prize winning theory. The equation captures how with each angle change, whether it's head-on, whether it's glancing, whether it's at a different angle, you get a different shift in wavelengths because energy difference is related to how hard the pool balls hit each other. What was so key about this experiment is it proved that photons actually have momentum. Waves do not have momentum. Momentum comes from being a real physical thing, what we would call classical mechanics. Just like the pool balls existing, you imagine them as spheres. Particles you can also imagine as really tiny spheres that kind of behave in the same way, just at a really small level with loads of them going on at once and loads of interactions happening. So this is actually light behaving as a particle. We have 2 for light as a particle, 1 for light as a wave. Remember, interference for light as a wave, and then photoelectric effect, and now Compton scattering for light as a particle. Also, side note, the reason this can't happen in waves is because if light was a wave, when the photon would hit the electron, a wave bouncing off it would come back at the exact same wavelength. Maybe it will be a little weaker in brightness, maybe it'll be a little less intense, but wave hitting another wave, there should not be a wavelength change there. So it gives evidence towards particle behavior. Okay, so now the girls are fighting. We have a bunch of people saying that light's a particle, and then we have the other side saying light is actually a wave. Which is the truth here? Why do we have all these experiments going on that show conflicting answers? Where does the answer lie there? Well, I hope the truth doesn't scare you much more. It's actually that light is both. But what kind of experiment can we even set up to show that light is both a wave and a particle at the same time? Actually doesn't look that different to the one we had at the start. We're back to our 2 slits, except this time, instead of shooting light, we're going to shoot electrons through them. Why electrons? We know they're particles. We know they have particle behavior at least. So you guys remember the interference pattern for waves, the dark fringes and the light fringes, because some waves add up and some waves cancel each other out. If we see that outcome, we know it's wave behavior. Now let's talk about the outcome for particle. We would see 2 stripes on the screen. Think of it as particles are like little objects that say little pebbles. You have 2 slits and you're just like throwing pebbles through each slit. And when you throw enough through, you'll end up with 2 stripes on your screen. So wave would be interference, particle would be 2 stripes. So they run the experiment with electrons. And this is the weird part. Each one acts like a pebble. You throw it through, oh, one place it lands, another place it lands. But when you build up thousands of electrons, you get the interference pattern for waves. So does that mean like a ton of particles add up to be waves? No, that's the trap. Each electron is still its own individual thing. It doesn't combine with the others to make a wave. The dots on the screen don't merge or smooth out into a wave. They stay together as individual dots. Each individual electron by itself, it spreads out, it goes through both slits just like a wave would, self-interferes, and that self-interference makes some spots on the screen more likely and some spots on the screen less likely for it to land in. When you fire 1 electron, you can't predict where it will land, but the odds of it landing in each following spot follow the wave interference pattern. Bright bands are where odds are high and the dark bands are where the odds are basically 0. So it's not that the wave is made up of loads of particles. The wave is the rule that each individual particle follows. And the pattern is the rule showing up once you have data points. You think that wasn't confusing? Now we get to the fact that particles, they know they're being watched. So same setup, electron interference, 2 slits. Are we going to see a bunch of dots adding up to a wave interference pattern? Only one difference to the experiment this time. At one of the slits, we're going to put a detector. What it's going to do is watch, record as each electron passes through it. And then what happens? The electrons just go through. They form 2 stripes, pure particle behavior. The wave pattern vanishes. The outcome of this isn't that electrons are sometimes a wave and sometimes a particle. It's that before anything is measured at all, they're in a superposition of both. It's in both states at once, going through both slits and taking both parts. This is what scientists call a superposition. What forces it to pick one path and then act like a particle is the act of information. This is the detector watching it. The moment which slit it goes through, information exists anywhere, it will turn into particle behavior. The electron commits to one path and the wave pattern disappears. It doesn't matter if a human looks at the detector readout or not. Once it's been detected, the electron commits and it becomes a particle. It's about the information existing in the first place. Reality doesn't commit to one answer until something forces it to. And quantum physics is the study of things at really small scale. Big things like tennis balls behave this way too in principle, but they're so big compared to an electron and interacting with so many things around them that the information about where they are constantly exists. So they're always committed. You only notice this superposition when something is small enough and isolated enough that the information genuinely doesn't exist yet.